how can this be happening? Let's take a look at this. So how are the principles of closure and continuity illustrated in this image? Right? Get the weird dude in the plaid. So if we take out all of the unnecessary stimuli, and this is an example in our textbook, this is what the doghouse actually looks like. So the principle of closure allows us to perceive this as boards as being continuous. Okay. And because now I'm knowing, I can see that this board goes in front, right? There's definitely a gap here. All right. Cool. All right. Depth perception and how we've tested for it. So depth perception, using both of our eyes, allows us to see in 3 dimensions, even though the images striking on our retina are 2-dimensional, and remember, upside down. But the key is depth perception allows us to judge distance. Okay, in a classic study by Eleanor Gibson and Richard Walk back in 1960 at Cornell, they came up with something called a visual cliff. So it was a model of a cliff with a drop-off area using a checkered board, but covered with sturdy glass. Okay. And essentially what they had the infants do, they put them over here in the back. Okay, and here's the sturdy glass. And 6 to 14 months, that's key. Anything earlier than that, the kids aren't going to see it. Were placed on the cliff and coaxed by their mother to come across. And most infants refused to. So this indicated to the Scientologists scientists at Cornell that they were able to, in fact, perceive depth. Okay, key to survival, I would imagine. Okay, and now we're going to go over some binocular cues and how they allow us to judge depth. So these cues are depth cues, such as retinal disparity and something called convergence, that depend on the use of both of our eyes. And as an object becomes closer or farther, both binocular depth cues operate to help us judge distance. I'll give you an example of both. All right. So we're going to do it a try it here. So what you guys are going to need to do is hold your 2 index fingers about 5 inches apart, or 5 inches in front of your face, I'm sorry. And the tips about 1/2 inch apart. All right. Now look beyond them. Everybody see a little sausage? And now what I want you to do is while you're still looking past your fingers, right? Move your fingers away from you. Okay. And your little finger sausage should disappear. Okay. Let's try it again. Okay. And so essentially by comparing the retinal images, our brain computes distance. So its nose is moving further away. Okay, and the greater the difference between the 2 images, the closer an object appears or is perceived. Okay, so the closer the 2 when you start off, it's further away. Okay. Okay, and the next up is something called convergence, which is the inward angle of the eyes focusing on your object. Okay, now we remember a combination from when we went over the anatomy, right? That's the lens focusing. And what this is our muscles telling us that something is getting closer. So if you will, a textbook or something that has writing on it. Okay. And what I want you to do is hold it out at arm's length. So I guess you could use your notebook. And while maintaining your focus on the letters, I want you to slowly bring this book closer to your eyes. And does anybody feel, it says pain, slight tingling or tightening sensation? If you do, these are the four muscles surrounding our eye, working to move our eye to focus, thus sending signals to our brain that the object in front of you is getting closer.
Yeah, I just felt it.
Mm-hmm. Okay. So we have convergence, so the muscle sending information to our brain to allow us to perceive something is closer, getting closer. And then, of course, our retinal disparity, comparing the two images from both of our eyes to compute distance. The greater the distance, the closer it is. Right. Okay. So those are our two binocular cues. We're going to go over monocular, meaning one, and this is on page 191 of your textbook, if you want to take a look for reference. So when things are further away, retinal disparity won't help, okay? Because there won't be much of a difference between the images cast on the left or the right of the retina. Okay, think of it like this. Even though this is the convergence, they're all going to be relatively the same. But as the images are getting closer, it's preserved to be closer. Okay, good. So we use monocular cues, which are depth cues available in each separate eye. Okay, to perceive depth. And the first up is something called relative height. And this is when we perceive objects higher and our field of vision is further away. And because we assume that the lower part of the figure or ground illustration is closer, we perceive that as the figure. So if I were to revert this image, which I did up here, okay, the black becomes the figure and the white becomes the ground, and vice versa. And it's only because of these being higher allows us to see that, okay? All right. Next up is something called interposition. So this is if one object blocks another, our view of another, we perceive it as closer. So in this example from our textbook, the deer blocking the tree trunk. Okay, so the tree trunk seems further away. Okay. Then we have something called relative size. So if we assume two objects are similar in size, most people perceive that the one cast with the smaller retina image is further away. So the assumption is that these two cans of insect killer are the same. Okay. The smaller retina image allows us to perceive it as further away, even though we know that they're the same size. We're going to get into that. Okay, anyone need more time? Okay, so what is linear perspective? And this is the use of parallel lines to meet in the distance. So the sharper the angle of convergence, the greater perceived distance. So again, the sharper angle of convergence, that would be here, is perceived to be further away as opposed to here. Okay. So the yellow sign and the car, which are further away from the two parallel lines of the road, seem closer together. However, the car in this image is close to where the parallel lines seem to come together, and so is essentially perceived as further away. Okay. So here's an example of linear perspective in our environment. Okay. Very close to the image on the front of our textbook. Now, in literally, okay, the distance between these never changes. Okay, because they're parallel. But we perceive them as converging, allowing us to see distance and depth. Okay. Okay. Where the railroad tracks meet on the horizon is something called the vanishing point. We have, of course, our horizon line here. And these uses of lines, linear perspective, okay, and our reliance on right angles allows us to perceive depth. Here's our vanishing point. The assumption is that these structures, assuming are columns, are physically the same size, right? So the front of this column is the same size as the back, but linear perspective allows us to perceive it as smaller than what it is in reality. And if you're taking notes on this, please make sure you add the reliance on right angles. Okay. And using all of those cues I had mentioned to understand that a smaller retina image is perceived as further away in combination with our linear perspective. All of these things are happening at the same time. Okay. Make sense? Yes, Mr. Carl. Okay. Okay, here we have an example of linear perspective in art. This is a flat surface